All right, so now we're ready to say a little bit more about Morse functions. So we talked about this idea of critical points and non-degenerate points. So let's try to put all this together. Okay, so at a critical point, all first partial derivatives, right, vanish. Okay, and so a local sort of Taylor expansion has no linear terms. Okay, and then if this critical point is non-degenerate, it's non-degenerate, then the behavior of the function in a small neighborhood of the critical point, right, is dominated by the quadratic terms. All right, so the intuition, if you will, is that if you do a multinomial Taylor expansion, right, then more or less that's saying that in all of the directions locally, right, there is a quadratic term associated with that. And so again, if the distances are small enough, right, all these quadratic terms will dominate. Okay, so that's more or less the idea, right? Whereas, for example, if some of the quadratic terms vanished, right, then it's possible that even when you're very close, it's like to the point where you do the Taylor expansion, you might have to worry about the cubic and higher order nonlinearities. Okay, and then it's like again the point is that if you do all this, if you have a critical point which is non-degenerate, then there's a local coordinate system where you can write everything again in terms of just the quadratic terms, right? So in local, so there exists, so if you have a critical non-degenerate point, right, non-degenerate point, then there is a local chart with where f has no higher order terms than quadratic. Okay, so this is what is called the Morse Lemma. Okay. Okay, so let U be a non-degenerate critical point. Of the function f from the manifold to the reals, right? Then there are local coordinates where U is at the origin. Okay. Such that f of x is equal to f at U minus x1 squared minus up to xq squared, right, plus xq plus 1 squared all the way up to xd squared. Okay, so there's some, more or less, it's like there are some directions. It's like where, it's like the second derivatives have negative sign, and some of them have positive sign, right? For every sort of x, which I write as x1 to xd, right, in a small neighborhood of u. Okay, and you've probably heard of the second derivative test, right? And so the sign of the second derivatives, it's like tell you something about whether something is locally minimizer, it's like, or a maximizer, it's like at least in that direction. Okay. Okay, so so the number of things with negative terms, it's like it's going to be significant. It's going to help us classify the non-degenerate critical point. Okay, so the number of minus signs in the quadratic polynomial is independent of coordinates. Okay, the specific, so this is independent of the coordinates, and it's called the index. Of the critical point. Okay, so in this case, the index of u is equal to q. So, so an index then classifies each of these non-degenerate critical points into d+1 types, right? Sort of non-degenerate critical points into d+1 types. Okay, so so for a two-manifold, for example, right, we have three types. Right, so we have minima, which have index 0. Okay, so you can sort of see that, right, because if it has 0 directions with negative values to this quadratic polynomial, then all these are positive. Then it's easy to convince yourself that f at u is a minima, right? You can have a saddle, right, so this is index 1, right? So in this case, the saddle has a direction where locally it looks like a maximum, and you have another direction where it looks like a minima. So it's called a saddle because if you have a horse saddle, you have some directions where the value is going up. It's like in some directions where the value is going down. It's like, and it looks like a horse saddle. Okay, and then that's the maxima, which has index 2. Okay. So you can, let me just remark that a consequence of the Morse lemma, right, is that non-degenerate critical points are isolated. The Morse lemma implies that non-degenerate critical points are isolated from each other. So they are basically separated from each other. Okay. So if you want to have an example, it's like of something which is not Morse, right? So the other remark is that, right, so this is not true. For functions which are not Morse. Okay, and the simplest example is, again, you look at the height function for the torus. Again, it's like, but where the torus is lying flat down, it's like on the surface, right? So you know that there's a critical value, it's like, which corresponds to the top, if you will, it's like of the donut, right? But that set of critical values, that set of critical points is not isolated, right? There's sort of this ring, basically, of points which all have this critical property, but they're not, they're degenerate, okay? So, yeah. So now it's like I'm able to formally define for you what a Morse function is. So, definition, Morse function right, is a smooth function on a manifold. Right, so F is a map from the manifold to the rails such that two things are true. So the first thing is that all critical points are non-degenerate. And the second thing is that all critical points have distinct function values. Okay. All right, and I should also remark that sometimes the second condition is relaxed. So sometimes the second condition is relaxed. Right. But we're going to require this, it's like for the purposes of our discussion. And sort of the reason, of course, is because it's precisely at the critical values where the topology of the sublevel sets change, right? So, so basically, it's like if you maintain the second condition that all critical points have distinct function values, then you're only going to get sort of one change, if you will, in the topology. It's like, and you don't have to worry about sort of multiple say homology classes being created or destroyed. Okay, yeah, so this just makes the sort of the calculations a little bit easier, and so that's why we'll maintain it, like for the purposes of our discussion. Okay, so let me just stop here for now.